Hi, everyone. Thank you for coming to my talk. My name is Nama Ben David, and I'm from VMware. Today, I'll tell you about our brief announcement titled Classifying Trusted Hardware via Unidirectional Communication. And this is joint work with Kartik Nayak from Duke. So the problem that we're studying in this work is Byzantine fault tolerance in general, and more specifically to solve agreement problems. And so it's well known that in an asynchronous message passing setting, Byzantine fault tolerance cannot be solved if the number of failures F is larger than 1/3 of the total number of processes N. So, and it's pretty easy to see why. So if we think of a setting with 3 processes total and one of them is Byzantine, it could be the case that the 2 correct processes receive different values. And now the Byzantine process, what it can do is actually send different values to each of the processes, pretending to have 0 when it communicates with the process that received 0 and pretending to have 1 when it communicates with the other process. And this technique is known as equivocation, where the Byzantine process sends different messages to different correct processes. What could also happen in an asynchronous network is that is a partition between 2 correct processes. So it could be the case that these 2 processes don't communicate with each other at all. And under this scenario, the correct processes have no choice but to each decide on their own input value. And so this would violate agreement. Unfortunately, this fault tolerance of less than 1/3 of the network is just simply not enough for some applications. So there's been a lot of work trying to increase the fault tolerance of Byzantine fault tolerant problems. And a very common technique is to augment the asynchronous message passing system with trusted hardware that sort of limits what the Byzantine process can do. And it's known that a lot of trusted hardware mechanisms can increase the fault tolerance from less than 1/3 to just under 1/2 of the processes in the system. And so we can still have the same situation where we have one Byzantine process and 2 correct processes that receive different inputs. There could still be a partition in the network. However, these trusted hardware mechanisms, generally what they do is that they prevent equivocation. So they basically force the Byzantine process to choose one value and relay it correctly to all of the processes that it communicates with. So this is the high level idea. However, there's been a lot of different ways to implement trusted hardware. And I just want to give you sort of an overview of the kinds of trusted hardware that exist, just to give you the idea that there really are many different ways of doing this. So there's a tested append-only memory, or A2M, which basically gives each process a trusted log that it can append to but never change anything in. And then it can also produce a trusted attestation showing that it did put something in its log. There's Trink, which is quite similar, and instead of a whole log, it'll just have a trusted counter that is incremented, and this incremented value is attached to each message. Then there are shared memory primitives. So there's PEATs, which is sort of a general way to say that you have objects that you can enforce specific access permissions for. So for every operation, there's a specific list of processes that can access this object with this operation. Similarly, there's sticky bits, which simply allow you to write once and never change this value again. Single writer registers have also been shown to increase fault tolerance for Byzantine settings. And similarly, RDMA, or remote direct memory access, basically gives different machines in a network direct access to each other's memory, and it can enforce access permissions similarly to single writer registers. And so this was just to give you a high level overview of the kind of mechanisms that exist, and there actually are quite a lot more in the literature. And so the question that we aim to solve in this paper is whether all trusted hardware primitives are actually the same in terms of the power that they give to a system. And we answer this negatively. So we show that they are not all the same. And in fact, what we do is we actually show 2 classes of these mechanisms, roughly construed as trusted logs and then shared memory primitives. And we show a separation between these 2 classes. So what we show is that shared memory primitives are strictly stronger than trusted logs. So the very high level idea of how we do it is we define this notion called unidirectionality. And we show that shared memory primitives can implement unidirectional communication, which in turn can implement a strong notion of reliable broadcast. And reliable broadcast can then implement trusted logs. And to complete the separation, we show that this strong notion or sequenced reliable broadcast cannot implement unidirectionality. So what I'll do for the rest of this talk is briefly define unidirectional communication and then show you how shared memory primitives can implement it. So I don't have time to show you all of these arrows in this diagram. So unidirectional communication, we say that a system can implement this if it's able to implement a notion of unidirectional rounds. So these are rounds in which every pair of correct processes must hear from each other. So either a process P hears from Q or vice versa. So there's at least one direction of communication between every pair of correct processes. So if we think of our original diagram for the beginning of the talk, what unidirectional communication does really is it still does allow a Byzantine process to equivocate if it wants, but it prevents a complete partition between any two correct processes. And what this does actually is it allows these processes to detect equivocation and therefore prevent it. So I'll now show you how shared memory primitives can implement unidirectional communication. The theorem that we show in our paper is that for any system in which it's possible to have objects such that for every process, there is an object that only this process can modify and all the rest of the processes can read, unidirectional rounds can be implemented. And this is true for all of the shared memory primitives that I showed you that have been shown to improve Byzantine fault tolerance. This is true for PEATs, sticky bits, single writer registers, and also RDMA. So at the very high level, here I have a diagram of the memory divided into these objects that only one process can write and all the others can read. And the idea for how to implement a unidirectional round is as follows. So if we think of two processes, P and Q, to participate in this round, to send a message, a process would write its new message and its round number into its object, and then go ahead and read all the other objects in the system. And if it sees any value with the same round number, then it receives that value. However, in this case, P didn't see any values without round numbers. So it says it hasn't received anything in this round. And it can move on to other rounds at this point. Now, if later another process Q wants to participate in round R, it will also write its new message into its object with a round number, and then read all the other objects. And here, Q will have seen the message M from P in this round, and so it is said to have received M from P in this round. And it's easy to see that it's always the case where if two processes participate correctly in these rounds, then at least one of them will hear the message of the other. And this construction is quite similar to a construction shown in an earlier paper of mine from PODC 19. But in our setting, we actually generalized it to general shared memory primitives. So this is unfortunately all I have time for. So I showed you this transition that shared memory can implement unidirectionality. I'll just give you a brief overview of what went into each of the other arrows in this diagram. So showing that sequenced reliable broadcast cannot implement unidirectionality involved a partitioning argument. Basically, we showed that with reliable broadcast, an adversary can still cause a partition between any two correct processes, so that violates unidirectionality. And this was the most technical part of the paper. Showing that unidirectionality implements reliable broadcast was a generalization of a reliable broadcast construction that appeared in that same PODC 19 paper that I mentioned. And finally, to show that reliable broadcast implements trusted logs, required first formalizing what trusted logs mean in general, despite there being several different implementations. And so I'll just leave you with this diagram and with a few open questions in this area. So first of all, we've shown the separation, but it hasn't been on a meaningful problem. So it'd be very interesting to see practical problems in which shared memory trusted primitives can actually solve something better or more efficiently than the trusted log trusted primitives. We also believe that unidirectionality could be interesting in its own right and could potentially find applications in different contexts. And finally, our initial question was whether trusted primitives all have the same power, and we've shown that the answer is no. But we do believe that there could be finer classification of trusted hardware mechanisms according to their power. And with that, I'll thank you for your time, and I'll be happy to answer any questions in the live sessions. Thanks.